to be talking about nuclear decay today. And nuclear decay is what occurs within the nucleus of an atom when that nucleus is unstable. It actually ejects certain particles in order to gain stability. And the nucleus of an atom might be unstable because it's too massive. There are too many particles for the weak nuclear force to hold the nucleus together. And also, there may be a disproportionate amount of protons to neutrons, so there needs to be a certain ratio of protons and neutrons in the nucleus in order for it to be stable, and when there's not, it will actually undergo a certain type of decay. And the three that we're going to be talking about today are alpha, beta, and gamma decay. Alpha decay, which is written symbolically when we're writing nuclear equations, with a 4 as the atomic mass, and a 2 as the atomic number. So this is how it's going to be written in a nuclear equation, where this is the atomic mass, which is protons plus neutrons, and this bottom number is the atomic number, which is the number of protons. Essentially, what is ejected from the nucleus during alpha decay is a helium particle. It's not really helium, but it's releasing 2 protons and 2 neutrons, which is a helium, without the electrons. It's also sometimes written with the alpha particle instead of the helium. This is a Greek symbol for alpha, but they mean the same thing. Okay, we also have a type of decay that's called beta decay, and beta decay we'll actually understand a little bit more about what this symbol means and why there's a negative number down here. But essentially, an electron is ejected from the nucleus, and it's more complicated than this, but for our purposes, you can think of it as a neutron breaking down into an electron and a proton, and then the electron is ejected and the proton stays. So the resultant atom that's formed from the decay will actually have 1 more proton in the nucleus. And then we also have gamma decay. This one is the easiest equation for us to balance when we're doing nuclear equations, because the atomic number and the mass number do not change. This is just going to be a high ionizing radiation particle that's released from the nucleus, but it doesn't actually release any protons or neutrons from the nucleus. It is also the most damaging of the 3 particles. This can penetrate deeper than the other 3. So this one is the one that you want to stay away from. This is the one that can cause a lot of damage to our bodies. Okay, I've got 3 nuclear equations written up on the board, 1 for each type of decay that we spoke about earlier, alpha, beta, and gamma decay. And we're going to learn how to balance these decay equations by looking at the numbers of the atomic mass and the atomic number on the left-hand side and on the right-hand side of the arrow. So on the left-hand side of the arrow, you have the original atom, what you have before the decay takes place. And what's written on the right-hand side of the arrow is the 2 particles, and of course I have a blank here because we're going to figure out what particle is formed through these types of decay. But you will see 2 particles that are formed from that type of nuclear decay. And this is pretty much going to be the easiest math that you do in your chemistry class, because all you have to do is make sure that the top numbers add up to the top number over here on the left-hand side, and that the bottom numbers on the right-hand side, the products, add up to be whatever this bottom number is. In this case, it's 92. So, knowing that, we know that 4 plus something has to be 238. And so all I have to do is say 238 minus 4 is going to be whatever this number is. Okay? So what I've done is said 238 minus 4 is going to give me the top number of whatever this symbol is going to be. So that's going to be 234. It's a 3. Okay? Same thing with the bottom. We've got a 92 over here. Something plus 2 has to be, be equal to 92. 90 plus 2 is equal to 92. So the bottom number, and the way that I found that was just 92 minus 2. Okay, the bottom number is 90. And the last step that I typically do is look on the periodic table. You need a periodic table in order to do these equations to find out what this element actually is. And so in order to determine what element the atom is, you just look at the atomic number. So look up on your periodic table. I have one right up here that you probably can't see. And see what atom has the atomic number of 90. And I don't know, you could probably see this one. But it is thorium. It has an atomic number of 90, the whole number. So I put the symbol TH right there. So I know when uranium, the U, undergoes nuclear decay, or alpha decay, it will form thorium-234. Okay? So again, just as a review, in order to know what this number is and what this number is, these two numbers have to add up to this number over here. So 234 plus 4 is 238. 90 plus 2 is 92. That's how I figured out what the numbers were. And then I used the bottom number, which was 90, in order to determine what the symbol was by looking on the periodic table for the atomic number. So let's look at beta decay. So that was alpha. Beta decay, we have carbon-14 undergoing beta decay, and we want to know what it will form when it undergoes this beta decay. So I'm going to do the same thing that I did for the alpha. 0 plus something has to be equal to 14. It's 14, right? Okay. And then negative 1 plus something has to be equal to 6. That's 7. Because 7 plus a negative 1 is 7 minus 1, which is 6. Okay, so this number has to be 7. Do the same thing that you did for thorium. Look on the periodic table for a 7, for the atomic number of 7. So that's going to be at the very, very top. And you see that that is actually going to be nitrogen. So when carbon-14 undergoes beta decay, it forms nitrogen. Nitrogen-14. Okay? Easiest equation I said that we're going to work with is gamma decay. And notice that this is a 0 and this is a 0. So something plus 0 has to be equal to 238. So that's 238, right? And then something plus 0 has to be equal to 92. So that's 92. And it's going to be the same element, because those are the same atomic numbers. So this is actually just high energy radiation. It's not actually a particle. Nothing's being released. It's radiation. So a lot of energy is being released from the nucleus in order to make it more stable.